Good morning. So today we are going to review those first three sections of Chapter 4 in preparation for a quiz tomorrow. And basically it's going to cover exponential growth, exponential decay, and also the exponential functions with the natural base of e, as well as those different formulas that we had looked at with reference to compound interest compounding continuously, and also just your basic exponential growth and decay functions. So this review will cover both the graphing and also using those formulas with some real life situations. So to go over the graphing first, basically we had graphing functions. We had both exponential growth, decay, and the ones with the natural base e, which were also growth or decay functions. So the first thing we'll talk about is just looking at those equations and reminding ourselves of whether they're growth or decay. So if you remember the basic formula for exponential growth and decay, it's a times b raised to the x. Now the big thing is if that factor here, that b value, is greater than 1, that's when you know it's growth. And if the b value was less than 1, but still positive, then it would be decay. And the a value always has to be positive. So if we look at this one here, the a value is positive. In number 2, the a value is positive. Number 3, the a value is negative. So this would just be a neither function, okay? Now for these two, obviously in number 1, the b is a growth factor because it is greater than 1. So we would know that number 1 is an example of exponential growth. Now when we look at number 2, we can see that the b value is a decay factor because it is less than 1. So this would be an example of decay. So make sure you can differentiate those different types of exponential functions. Now, in all three of these, there's no h or k values, so the parent function is really the function that's right there that we're going to graph. Now, you're more than welcome to use your calculator as you're doing any of these graphs and utilizing that, so you don't have to write down this whole little table of values every time. I'm doing it just so you can see where I'm getting my points, but you can totally use your graphing calculator for that. Okay, so as soon as you see your function that you're going to graph, you've identified it as a growth function. We know the growth factor is 12 here, and the a value is positive 2/3. So if you want to, you can always fill in all this information down here at the bottom before you even really do anything else. Now, if you remember, the domain for these on every single graph on this page is all real numbers. The range and the asymptote go hand in hand, right? So if there's no k value adding or subtracting to the end, we know the asymptote is y equals 0. And then your range will be y is greater than or less than 0, depending on that a value. Since my a value is positive, my range is y is greater than 0. The y-intercept is what you get when you plug 0 in for x. And because these three equations on this top part here, 1, 2, and 3, none of them have h or k values, so it's just that a value, which in this case will be 2/3. You don't actually have to do too much for that. So we know that's 1 point. Then if you want to find any other points, you can use your graphing calculator, or you can just plug them in and get them off your table values. So if I were to plug in, let's say, a 1, for example, 12 to the first power is just 12, and what's 2/3 of 12? That's 8. If I were to plug in a -1, that would flip my 12 to the bottom, and I would have 2 over 36, which is 1 over 18. If I were to put in, let's say, a 2, I would get 2/3 of 144, and that's going to be a big, those other numbers I'm not really going to be concerned with. Okay, so now graphing this here, I have -1 and 1 over 18, which is a very small decimal. Then I would have 0 and 2/3, and then 1, 8. 1, 2, 3, 4, 5, 6, 7, 8. Wait. And that would be there. And we know an exponential growth function is going to look like this. Now, of course, our asymptote is just the x-axis in this case because it's just y equals 0. So now if we go to the next problem, which we know is a decay function, so it's going to kind of look like that. Again, there's no h and k here, so there's no shifting that's going to happen. So then we know that the y-intercept is just 0, and then that a value, which is positive 4. The domain is always all real numbers for these graphs. The asymptote in the range, because the k value is 0, you have y equals 0 for the x-axis for your asymptote, and then y is greater than 0 would be the range, meaning your graph will be above that asymptote. So now if I want some more points on here besides 0, 4, I can use my calculator to get a table of values here. So I know I have 0, 4. If I want to put in, let's say, a 1, then I would have 1/4 times 4, which is 1. If I want to put in a 2, 1/4 to the second power is 1/16. And when I multiply that by 4, I end up with 1/4. If I did a -1, that would flip my 1/4, and I would have positive 16. So -2 is going to be off the graph anyway. So -1 and 16 is way off the graph somewhere. 0, 4, 1, 1, and then 2 and 1/4. So you can get the idea that the graph is going to look something like that. All right, and then moving along to our third one with our natural base of e. Okay, so again, domain still all real numbers. There's no k value here, which means it's 0. So my asymptote is still y equals 0, and my range would be y is less than 0 this time because of the negative a value. Now my y-intercept, when I plug in a 0 there, I'm just going to get -2. Because again, anything raised to 0 is 1, and then that's why you end up with just your a value for the other part of that y-intercept. So now making a chart or using your calculator here to get the chart. So just as a refresher on the calculator with the e value, you have here -2, and then you can use second, and I like to use the shift from the ln, which already has the e raised to a power, and we know it's going to be 0.5x, and then I can graph it if I want to see what it looks like. We know that it's going to be going down because of that negative a value. And then if I want some points off my table, I have, okay, -1 and -1.2. So we know -1 and -1.2 will be right around there. We have 0, -2. And then I think if we go to +1, it's -3 point something. And then if we go to +2, it's -5.4. Okay, so we can kind of see it's starting to emerge there. All right, so that's basic graphing when there's no h and k. So now the bottom 3 graphs are going to have h and k values. So if we take a look at these, we want to identify that information, right? So if I take a look at number 4, for example, okay, so my h is the number being subtracted from the x, so my h is going to be +2, which is going to shift it 2 to the right. My k in this case is -1, so that would be shifting it 1 down from the parent function, which we're going to graph the parent function first. The y-intercept, we will have to plug 0 into the entire equation and find that, so we'll get to that in a bit. The domain is still all real numbers. My asymptote this time, since I have a k value, it's y equals -1, and then the range will be y is greater than that -1 because the a value is positive. So now, if I'm going to graph my parent function, I'm going to just do this highlighted portion here because I can make a table for that much easier than trying to do the whole thing. So if I make my table for this, okay, I know it's going to be 0, 2. I know if I have a +1 there, I'm going to get a 10. +2 would be 50. A -1 would make that 2/5, and a -2 would make that, I believe, 2/25. Yes, 2/25. So 250 over 2, up 50 is off the graph. Then we have 1, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, 2, negative 1 and 2/5, and then negative 2 and 2 over. All right, so this is our parent function right here. Now, if I want to shift that to get my actual function, we're going to shift everything 2 to the right and 1 down. So this point up here, I'm going to go 2 to the right, 1 down. This one here, 2 to the right, 1 down. This one, 2 to the right, 1 down. This one here, 2 to the right, 1 down. So you might be able to tell what this y-intercept is, since I was shifting that point 2 to the right and 1 down. But if you want to write 0.92 or negative 0.92, that's what it will be if you plug the 0 in for x and solve it out. If you have a fraction answer, that's fine too. Okay, so let's take a look at the next one. So again, our next one, our parent function is just up to there. So if I'm going to enter all this information first before I do the graph. So my h here is negative 3, which means I would shift 3 to the left. My k value is positive 6, so I will shift 6 up. My y-intercept is whatever I get when I put in that 0. And my domain is all real numbers. The k value is 6, so my asymptote will be y equals 6, and my range will be y is greater than, or no, wait, is it a negative there? Yeah, it's a negative, so it's less than 6. Okay, and then putting in the 0, I'll just see what happens when I do the graph, because sometimes it just shows up on the graph, and then I don't have to do that extra work. Okay, so graphing my parent function first. I know I'm going to have 0 and negative 1. Now, if I put a 1 in here, I will just have negative 1/2. If I put a 2 in, I'm going to have negative 1/4. If I had a negative 1 in, I would have negative 2. And if I have a negative 2 up there for x, I would have, let's see, that's going to be 4, negative 4. So my parent function looks like this: negative 2, negative 4, negative 1, negative 2, 0, negative 1, 1, negative 1/2, 2, negative 1/4. So this is my parent function right here. Now I'm going to shift each of those points 3 left and 6 up. So 1, 2, 3, 1, 2, 3, 4, 5, 6. Then this one, 1, 2, 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. And then the next one, let's see, 1, 2, 3, 1, 2, 3, 4, 5, 6. It's kind of like that. And we know that the 6 is going to be our asymptote, so it's going to kind of level off there. All right, so again, this y-intercept, we probably have to just plug 0 into the whole thing and calculate that out. It is going to be a decimal. It works out to be about 5.8 if you do it on your calculator. All right, and then finally, let's do the third one here. So now this one is a continuous one. So right here, we're looking at our h value, because remember, this is the r here that's getting multiplied to this. So this is my h. So h is going to be negative 4, which means I'm going 4 left. My k value is negative 7, which means I'm going to go 7 down. Domain, all real numbers. Asymptote, y equals negative 7. And my range here is going to be y is greater than negative 7. And when I plug in a 0, I'm going to actually get negative 6.9 if you want to go ahead and do that on your calculator. So now doing my parent function here. And that is going, actually with these ones, you're just going to graph the whole thing. Remember, because you could graph it, but you're still going to have to use the calculator anyway. So it seems silly to do it once and then have to shift it anyway. Since I'm already using my calculator, I'm just going to go ahead and do that. So let's see, for some reason my paper is not showing up very well here. So we have 3e raised. So 3e raised. Now I have a negative and then a parenthesis, and then it looks like it's x plus 4. X plus 4, close the parenthesis, and then we have just that minus 7 at the end. Okay, so we can get a sneak peek of what our graph's going to look like. And then if I want to go to my table of values and get a few things off there. Okay, so we know that's going to level out at that negative 7. See if there's any other points that are a little farther. Okay, so -4, -4, -5, and 1. So if I go -5 and 1, that's approximately one of the points. 1, 2, 3, 4, 5, about here. Then we had -4, and I think it was -4, right around there. Then we had -3 and -5.89. 1, 2, 3, 4, 5, so maybe right there. And then everything after that kind of started, let's see, we had 0, -6.9. 1, 2, 3, 4, 5, 6, so right around there. So, just plot whatever you can. And it looks something like that. So hopefully that helps you out with any graphing. It's pretty straightforward. A lot of the stuff is similar no matter what type it is. The biggest thing is identifying which ones. Now, just getting back to that with those E values. So if you remember that the R value is the number in front of the X. So our R value here is -1. And when the R value is -1, that's decay. When the R value is positive, that's growth. So this was a decay function. So that's obviously what we saw there. Now, when you go back up to number 3, for example, let's say that was a +2. Well, this time my R value was a positive, so that would have been a growth function. So just keep that in mind as well. Okay, then finally, we're just going to do a few practice problems with the different formulas. The formulas are over here on the left-hand side. Obviously, when you take your quiz, the formulas won't be given to you with the problem. You'll have your notes accessible. So, maybe pull up the, I'll probably actually put a PDF of all the formulas if you want to have that pulled up on the side or something. If not, you can just go through your notes and get them out of there. Okay, so you have inherited land that was purchased for $30,000 in 1960. The value has increased by approximately 5% per year. Write a model that describes the value of the land T years after 1960. Okay, so to figure out the different formulas, the first thing is if we see increased by process of elimination, it's not a decay function, right? Decay function will only be used when it's a decrease or depreciation, something going down. When it's going up in value, it's definitely not that. Then the formula with the E in it, that is down here on number 4, that is obviously only used when you see the word continuously. So that's how I would know I would use this formula. Then for number 2, you can see how it talks about things being compounded at different time periods. So when it's compounded at different specific time periods, that's when you're using this bigger formula here on the left. And then number 3, we're talking about 12% of the air is replaced. So write the model for the amount of original air left. So obviously we know it's decreasing. But this formula is this problem is a little vague. Usually you'll probably on the quiz have one that will actually say the word decreasing, so you'll know. Anyway, okay, so back to number 1. So you've inherited land that was purchased for $30,000. So that's that starting value here. This is your A. Then you have this 5% per year. So you know the R, the R is, oh my goodness. The R is going to be 0.05. Be careful because the one mistake people make is they forget how to move their decimal on percents. It's always 2 spaces to the left from where the percent sign is if there's no decimal. So if it's already a decimal number, like let's say you had 5.5%, you're still moving the decimal 2 to the left. Okay, so in 1975, this is going to be 15 years later, so that would be T equals 15. In 1998, you're going to have a t equals 38, because that's 38 years later, and in 2009, your t would be 49. Now, you can definitely, the model that we're going to use here is going to be 30,000, and then 1 plus 0.05 raised to t. And obviously, we can simplify that to be 1.05. Now, you can individually enter this in your calculator 3 separate times, putting in the different t values, or you can just put it into your graphing calculator using the variable there, and it'll give you all the answers if you just scroll down your chart. So it's completely up to you. So if I go to my y equals, and I put in my 30,000, and now I'm going to do 1 plus 0.05, which is just 1.05. And then if I raise that to t, whoops, or x, it's always going to show up as an x on your calculator, and you go to chart or table, now I can see all the years. So the first one I needed was 15 years later. So I'm going to scroll all the way down to 15, and I see it's 62,368. So 62,368. You should get basically the same answer if you did on your calculator individually. Now we want to scroll down to 38 and then 49. So if I scroll all the way down to 38, the only downside to doing it this way is the scrolling if you have a high number to go to. And that's 191,564. And it was actually 32 cents if you did it individually. And then 49, and if you don't have that cents, it's fine. It'll be multiple choice anyway, so you won't have to worry about that. 327,640. And there you go. So I would recommend doing it that way. You get all 3 answers in one shot. But if you want to enter them separately because you don't have your graphing calculator or something, then you can do it that way as well. Okay, so number 2 is a little more specific. You could technically use the same formula. However, this original formula that we just used in this problem is only for things that happen like once a time period. So this was talking about the increase of the land each year. So if the rate is an annual rate and then you're talking about each year, then that's what you would use. But the next problem, we're getting a little more detailed because it says find the balance after 3 years, but then it talks about the interest being compounded at different times. So that means the interest is going to happen more frequently than once a year. So we have to account for that. So for this first problem, it's compounded monthly, which is an n value of 12, but everything else is the same. So your A is going to be the 1,600. Your rate is going to be 0.025. Be careful because a lot of people make a mistake and they write 0.25 and then everything's wrong. So make sure you're always moving that decimal 2 places to the left to go from percent to that R value. So when we put this in our calculator, basically you're going to have your principal, which is 1,600, times 1 plus that rate written as a decimal divided by your n value. And then the exponent is the n value times however many years, and we're doing this for 3 years. So when I put this in my calculator, I'm going to do the parentheses portion first, right? So my parentheses portion here, I'm going to do the this part first, right? Whoops. On there. Okay, so I'm going to do this part first right here, the 0.025 divided by 12. So 0.025 divided by 12, add the 1. So that's what we have in, oh, shoot. All right, let's try again. Sometimes I hit the wrong button. Okay, 0.025 divided by 12, add 1. Okay, so now that's what's inside the parentheses. We want to raise that to this 12 times 3, which is obviously 36, right? So we raise it to 36. It equals again. Then multiply that to that initial value, which was 1,600. I would recommend doing it that way versus trying to put the entire thing in your calculator at once with all those parentheses. So we get 1,724 and 48 cents. 1,724 and 48 cents. Make sure you're doing it in dollars and cents, okay? All right, next one, we're talking about compounded quarterly. So that is an n value of 4. That means 4 times a year. So you're still doing the exact same thing, 1,600 times 1 plus 0.025 over, but it's over 4 this time, and then my exponent is 4 times 3 instead of 12 times 3. So when I put this one on my calculator, I'm going to do the 0.025 since that's my rate, but this time I'm dividing it by 4. Then I'm adding the 1, and then when I raise it to my power, I'm raising that to 12 because 3 times 4 is 12. And then I'm multiplying that by the original amount, which is the 1,600, and I get 1,724 and 21 cents. Okay, so now it makes sense because the more frequently the interest is compounded, the higher your money will go up. So if this is compounded monthly, that meant you got it 12 times in the year instead of 4. That's why that's a slightly higher amount. So the cents value is important for these. So don't just round everything to 1724. Make sure you're looking at the cents as well. And now daily, this would be an n value of 365. So we're doing the same thing. Same formula, but we're just going to put in 0.025 divided by 365, and then 365 times 3 is our exponent. So when I go to my calculator, I'm going to do my 0.025 divided by 365, add 1. Now I have to raise this to 365 times 3. So I put it in parentheses because I didn't know what that was off the top of my head. If you already did it on the side, then just raise it to the number. And now that's getting multiplied to that 1,600. So 1724, 61. 1724, 61. So you can see that that's a little bit higher of a value than the monthly interest. Okay, so number 3, like I said, typically the decay problems, you're going to see something about like, you buy a car and it loses value or something like that. In this case, we're talking about the air in our lungs, so it's decreasing. So when the air is 12% is replaced, that means you're losing that 12%, and then that's going to be replaced with the next breath. So your initial amount is the 500 milliliters here. Then you're going to do 1 minus the 0.12, and then you're going to raise it to 10 because it's 10 like repetitions of this. So in a money problem, it'd probably be like 10 years. In this case, it's 10 breaths, I believe. So when you do this one on your calculator, the model is 500 times, and then this is going to work out to be 0.88, which makes sense because decay value, remember the decay factor is less than 1. So now we're going to put this in the calculator. So I'm going to do 500 times 0.88 raised to 10, and that's 139.25 milliliters. And then I'm going to do it again for 20 breaths. So I'm going to do 500 times 0.88 raised to 20. And I get 38.78. And of course, you could have also done it on your graphing calculator. So what that means is after 20 breaths, you only have 38.78 milliliters of the original breath that you took, or the initial amount of air. All right, and then finally, the big thing here is if you see the word compounded continuously, that tells you you're using this formula. To me, that's like the easiest process of elimination problem. You see the word continuous, there's only one formula appropriate to use. So then, you're just plugging it in. Okay, so for 3 years, 6 years, 11 years. So when you're figuring this out, your initial amount is 975. Then you're going to do times E raised to 0.55, be careful with those, times, and then whatever the years are. So that's going to vary. So now whether you want to enter this separately for each problem, putting in the number of years, or you want to do it on the graphing thing and then look them up on the chart, you got the option, right? So if I go to my y equals, I'm going to type in 975 times my e, and I'm raising that to 0.055 times t, or x, whichever variable, and I'm going to hit my chart, right? So I have to scroll back down because I need 11, 6, and 3. Okay, so we see the 11 is 1785.50. 1785.50. Then if I go to 6, it's 1356.20. And then if I go down to 3, it's 1149.90. All right, now if you worked it out individually, your answers might be like, I think it's 0.91, 0.19, 0.47. That's fine. Again, the choices on the quiz will be multiple choice, and I'm not going to put them off by 100th or anything like that. So it shouldn't be an issue. All right, so again, use your notes and your formulas to take the quiz tomorrow. Make sure you message me if you have any questions or concerns about anything. And that's about it. Otherwise, enjoy the rest of your day. Thanks.